Now we will see what's vector space. A vector space it's a collection of objects called as the vectors which may be added together or multiplied by numbers called scalars. This is the definition. Then what is this vector space? Here we can see that this is one vector and this in some vector space W and 2W. It is a scalar multiplication. Okay, in simple words we can understand what's this vector space with this definition. It's the collection of vectors v means lots of vectors v1 v2 v3 like that, and two operators plus and multiplication, and that the following holds for u v w belongs to v. Means if we draw the small vectors like u vector, v vector, w, then these are all vectors belongs to that vector space, collection of vectors means vector space v. And if we used any scalar constants for scalar multiplication, so in the definition it's given as c and d belongs to the real numbers. I think you get confused. Now we will visualize that what's actually the real vector spaces. So yeah, it's a collection of vectors, means there are lots of vectors. It's a collection of many vectors, and importantly it should satisfy the 10 axioms. I will explain the axioms, then we will see what is actually the vector space. You'll come to understand. So if we have many vectors like u vector, let's say it's a u vector and it's v vector. If you want to call these vectors u vector, v vector, and here we will draw on w vector. Okay, this is a vector. If we want to call this as a vector space, then it should satisfy, that means these three vectors should satisfy the following axioms. Means if many vectors are there, then that they should satisfy these axioms. Let's discuss those axioms one by one. There are 10 axioms. The first is the first axiom, that's vector addition. Vector addition. Vector addition means if you have any two vectors u and v vector, u vector and v vector, then the summation of these two vectors u vector plus v vector should belongs to the v. That means the summation of these two vectors gives some vector. That vector should be in this vector space. If we call this as a vector space v, then the summation of u vector plus v vector, that should be in this v vector space. That's the axiom 1. And the second one is the scalar multiplication. Scalar multiplication means if we have any constant, let's call it as a c. Okay, let c be a constant. If we multiply this c to the any one of the vector, then we will get some vector. That means the resize. If this is my vector u vector, I am multiplying 2 with this u vector. That means 2 times u, this much plus this much, u vector. This vector should be in this vector space. If we call this small u, this u vector is a vector space, then 2 times of this u vector, 2 times of this u vector, this vector should be in the vector space. That's the scalar multiplication. That should be belongs to v. Okay, then we have something called commutativity. That I think you know that commutativity. If we have the two vectors, then if we add those two vectors, u vector and the v vector, that's u vector plus v vector, that's equals to v vector plus u vector. That's it, commutativity. Okay, means it's like if we have one, there's a u vector and this is a okay, I will take like this is a v vector. Okay, then if we add these two vectors, we will get, I think you know this parallelogram vector addition, you will get something, the resultant vector is like this. So instead of this u vector plus v vector, now I will consider v vector first, then I will consider u vector. Then also we will get the same resultant, that's the like this, that is the u vector plus v vector. Here both these are equal. If these two are equal, then it satisfies the commutativity. That means it satisfies this axiom. These two vectors satisfies this axiom. Actually, if you want to call those vectors are in a vector space, it should satisfy the 10 axioms. The next one is the associativity. We'll see that associativity or associative property. Associativity of addition we will see now. Associativity means it's a u vector plus v vector, I'll put a bracket for it, plus w vector is equals to, if it is equals to u vector plus, I'll put a bracket here, v vector plus w vector, then we will call this as it holds good the associativity. If you take the three vectors, for example, yeah, here I took the two vectors, u vector plus v vector, the resultant is this one. Now I will add w vector for this resultant vector. That means this is the u plus v vector, and okay, this is my u plus v vector, and now I will add another vector, that is w vector, then the resultant of these two, like this, it is a u vector plus v vector plus w vector. Okay, then now what I will do means I will add v vector plus w vector first. So here I have two vectors, v vector plus w vector, this is v and this is w, the resultant is v vector plus w vector. Then I will add this v vector plus w vector with the u vector. Okay, then this is our v vector plus w vector. I will add this one with the u vector. Here you can see that u vector is this. Okay, here I will add with the u vector. Then again we will get the resultant, that is equals to u vector plus v vector plus w vector. These two vectors are equal. We can see this one and this one. These two are equal. So it holds good the associativity. You have to remember this, u vector plus v vector plus w vector equals to u vector plus v vector plus w vector. Then the fifth one is additive identity. Additive identity means if we have any vectors like a u vector, then if we add something to this, okay, it should give u vector only. That's the additive identity. Then what if we add to this u vector, it will give the u vector itself. If we add the 0 vector, then u vector plus 0 vector give the same u vector. That's called as the additive identity. If we take any vectors like x1 vector comma x2 vector, these are all which belongs to, in generally we are calling this as u, so which belongs to v, this is the main vector space. These are all the small vectors, this belongs to v, and we have 0 vector that belongs to v. Then if we add these two, u vector plus 0 vector, then you will get the u vector. This is the additive identity. The next is multiplicative identity. Multiplicative identity. If you multiply any vector, for example u vector which belongs to v, okay, if you multiply this u vector with the one vector, then we get the same vector, u vector. This is the multiplicative identity. That means if you multiply any vector by this scalar 1, then we will get u vector. And next one is the additive inverse. Additive inverse means for all the vectors which belongs to the vector space V, we have a vector that is minus u vector. That is the additive inverse. That means if we add u vector with this additive inverse plus minus u vector, then we will get 0. This is the additive inverse. Then we will see the some confusing axioms. That's a distributivity of multiplication. Next one is the distributivity of multiplication. Here C is our scalar which belongs to some real numbers. If I tell anywhere these constants belongs to vector space V, instead of that we can say the C belongs to R. Okay, this is one constant. Then we have C into U plus V equals Cu plus Cv. This is the distributivity of multiplication. If this vector u vector and the v vector with this scalar c, if it satisfies c into u vector plus v vector equal to cu vector plus cv vector, then we call this as it satisfies the distributivity of multiplication. Next one is the distributivity of multiplication. Distributivity of multiplication over addition. Distributivity of multiplication over addition. Here let C1 and C2 which belongs to real numbers. Then anyway we know that C this u vector which belongs to the vector space V. Then if it satisfies C1 plus C2 into u vector equals to C1 into u vector plus C2 into u vector, then we call this as the distributivity of multiplication. Next one is not the multiplication, distributivity of multiplication over addition. The previous one is the distributivity of multiplication, and this is the distributivity of multiplication over addition. And the last one is the associativity of multiplication. That we know if we have any constants C1 and C2 which belongs to real numbers, then C1 into C2 into U is a vector which belongs to V equals to C1 into C2 into U. Okay, this is the associativity of multiplication. Now we will clarify what's this vector space. Actual means some practical applications. What is this vector space is? So if we want to call some vectors as that belongs to the vector space, it should satisfy all these 10 axioms. But instead of that, if we check the vector addition and scalar multiplication, only two axioms. Vector addition, that means vector addition, that is u vector plus v vector, which should belongs to V vector space, and the scalar multiplication, that is any constant which belongs to R, C into U vector, which belongs to vector space V. If we clarify these two, then we can call that as the vector space. So now let's see some practical examples, like we'll understand now what's the actual meaning of vector space. If V equals to x comma y, where x equals to 0 and y equal to 0, is this a vector space? The question is like this: is this a vector space? Now we will visualize. Okay, this is our x-axis and this is the y-axis. They told x equal to 0 and y equal to 0, means that should be in this plane, x comma y. Okay, that means all the vectors that present in this or vector space, they are asking like this: all the vectors they present in this what's that, x equal to 0 and y equal to 0, this quadrant is called as the vector space. We will check it. If we have the vector like okay, I will draw here this x and this y. Okay, if I have one vector like a vector is like this is my a vector, and if I have another vector like I have another, okay, b vector, then a vector plus b vector, we need to check these two axioms. Remember this: vector addition and scalar multiplication. Okay, here I will check this vector addition, a vector plus b vector, that will give me the vector like this. This is my resultant vector. This belongs to the first quadrant, that means this r vector is in the first quadrant only. R vectors also satisfy x equal to 0 and y equal to 0. Okay, one axiom satisfied. Then next one, scalar multiplication. So for that, if we take the c, that means c belongs to R real numbers. Real number means it may include the negative numbers. So what I will take means c equals to -2. So this is my a vector. Okay, now what I will do means, yeah, I will show here. This is my a vector. I will consider like this. Now I will multiply c into a vector. Then what I will get if I multiply this c into a vector? C is equals to -2. -2 into a vector. That means it will come in this way. This side, in this quadrant, it will come -2 into a vector. It is in a minus, so it does not, this resultant vector is not in the first quadrant. That means it is not satisfying x equal to 0 and y equal to 0, the given condition. So we conclude that this question, or this x equal to 0 and y equal to 0, this is not a vector space because it doesn't satisfy the scalar multiplication axiom. Then if the question here, instead of x equal to 0 and y equal to 0, if they give x, y is greater than 0, then we may include this now, this and this, these two. So if we consider the first axiom, this axiom, then it will satisfy the vector addition. Okay, if we consider this second one, then also it will satisfy, because now this is minus, this is minus, minus into minus plus, xy is greater than 0. Okay, but if we carefully think about this, if I draw one vector like this is my a vector and this is my b vector, then if I add these two, a vector is in the given v, that means given vector space, b vector also in the given vector space. If I add these two, I will get something like this. This is not in the any of these quadrant, this or this quadrant. So we conclude that this is also not a vector space. If it satisfies the vector addition and the scalar multiplication, we have to call that as a vector space. We should remember that this should satisfy the 10 axioms. And these vector spaces are usually represented by R1, R2, R3 like this, Rn. N components. N represents the, it means n components. R1 means it is actually one dimension vector. R2 means 2 dimensions. 3 means something 3 dimensions. We can visualize that like this. Here we can see this is a R1 and this is R2, this R3, R4, R5, like this. It's a 5 dimension, but usually we can see only up to the 3 dimension, but there are some 4 dimension, 5 dimensions are there. So this is denoted by R1, R2, R power 3 up to R power n. Now again, if we look the definition of this vector space, I think you can understand now. It is the collection of vectors v and two operators plus in the multiplication such that the following holds for the uv belongs to v. Following means the axioms, these 10 axioms belongs to v and cd belongs to r. A vector space is a collection of objects or the vectors which may be added together and multiplied, scaled by the numbers, called scalars. If any vectors are given, if they satisfy the vector addition and the scalar multiplication, then we can say that those vectors are in a vector space. If they give the condition like we saw that xy is greater than 0 and x equal to 0 and y equal to 0 in these two problems I discussed now. If they give the conditions like that, then we need to check whether the scalar multiplication and the vector addition that satisfies in that condition. That's it, the vector space. Thank you.